So I will present indeed the PLATO mission. I'm an Heras project scientist of PLATO at ESA. And I normally, of course, present PLATO on behalf of the many PLATO teams that are really developing the spacecraft, both from the hardware point of view, the software, and the scientific point of view. And I also have highlighted here the name of Don Polaco. Don is at the University of Warwick, and then he's the leader of the science management at the consortium. And I also discuss a little bit with him, the contribution from amateur astronomers to the mission. Okay, so just to start, so what is PLATO? Well, just to say it in one sentence, so PLATO, which is an acronym for Planetary Transits and Oscillations of Stars, is a mission to detect and characterize exoplanets and study their host stars. And is the third medium-class mission of the program Cosmic Vision at ESA. I will continue by saying, well, okay, why do we need another exoplanet mission? I mean, why do we need another mission to characterize and detect exoplanets? Well, first, one of the main problems that we have is that we have indeed detected and confirmed a lot of exoplanets. So we have around 5,000. I put here always approximately because every day it increases. But then they are mostly detected around stars that are not very bright, and that's why it's difficult to characterize them. So we really need to detect more exoplanets around bright stars for exoplanet characterization, especially for small exoplanets. So here I have put a figure where you can see the number of planets as a function of stellar optical magnitude, for which we have radius, which is indeed the histogram in blue. Then for which we have mass, which is the histogram in brown. And then we only have an overlap of planets for which we have radius and mass in the red area. But if we go to smaller exoplanets, so to planets that have a radius of less than 2 Earth radii, then we only have this small green area, which means that indeed the number of small exoplanets for which we have radius and mass is still very small. And if we want indeed to find more about their diversity, and also if we want to characterize them, for example, their atmospheres, then we need to find more around bright stars. We also need higher precision, because it's not only a question to detect and see the transit, but also to be able to characterize the radius and also characterize the mass. And of course, the brighter the star, the better we can do this also. And also, we need an instrument that allows us to go to lower or to much better precision, to lower uncertainties. And then that's why here I represented the diagram of radius versus mass. The different colors are models for exoplanets that will be made of water, or 50% water, or iron, or 50% iron, etc., as it's represented here. And the dots represent the planets for which have less than 30% uncertainties in radius and mass. So that's why the green area we have seen before, now we put it here, but only for the ones that we know best, their characteristics. But you can still see that indeed the uncertainties are relatively big. So we don't know, in some cases, well, the composition, because uncertainties are large. And also, as you can see, close to the area where the Earth and Venus are, the number of dots are reduced, because indeed we have not detected still exoplanets of this size, and we have not been able to characterize them with their masses as we need to indeed put our solar system in context and understand much better the diversity of exoplanets. Okay, then I wanted, of course, to introduce another concept, which is the habitable zone. And we normally define the habitable zone around the star as the area around the star in which a planet that orbits around can have water in liquid form on the surface of the planet. And so if the planet is too close to the star, the water evaporates. And if it's farther, then it's in ice form. So that's why we call the habitable zone in this, for instance, this area around the star, in which the water can be in liquid form. Then if we take indeed the small exoplanets that we have seen before, so the ones with less than 2 Earth radii in size, and then we represent them now as a function of the distance of the star, and also as, I don't know if you hear this, I hear an echo. Can you hear it also?
Yeah.
Yeah, okay. So maybe, thank you very much, because it's a lot of noise, it was noise in the background, thank you. Okay, so then if we represent these small exoplanets as a function of the distance of the star, then we see that most of them are very close to the star, indeed, for all the stellar masses. And then actually they are all in orbits that are like inside the orbit of Mercury. And then this implies that indeed we have some small exoplanets in the habitable zone of very small stars, that M dwarfs, but actually we still practically don't have any characterized exoplanet with radius and mass in the habitable zone of Sun-like stars, like is represented here by this green area. Okay, so then all these reasons bring us to indeed the need to have another satellite, to have another spacecraft that can probe the bulk properties, we hope, of hundreds of exoplanets, and that includes terrestrial planets in the habitable zone of Sun-like stars. Because indeed the missions that we know until now, and then the ones that are in orbit like Cheops and TESS, will characterize these exoplanets, but mainly in the area which is indeed closer to the star, so then in regions that are not in the habitable zone of Sun-like stars. But we also, as I said, we need very good accuracies. We really want to characterize these small exoplanets much better. And of course, if we can do this with the small exoplanets, for the larger planets, the precisions will be even better. The required planet properties accuracies that we have in our requirements is that we would like to have a radius measurement of 3%, a mass measurement of 10% uncertainty, and an edge uncertainty of 10% for an Earth-sized planet orbiting G0 dwarf stars with magnitude less than 10. So then this is the main driver requirement for PLATO. And from this requirement, then we derive all the other requirements and we build a mission. If we achieve this, then we really can study with a lot of detail planet evolution with age. We will learn a lot about the internal structure of stars. Then we can also investigate in depth architecture, formation, evolution of planetary systems and how they correlate with the stellar parameters. We can identify then good targets for a spectroscopic follow-up, because as I said before, we need exoplanets around bright stars to be able to characterize them, and even more if we want to do atmospheric characterization. So PLATO will not do atmospheric characterization, but can provide targets to the GRACE facilities that are coming in space and on the ground to do this job. We will also be able to address additional planetary science, so very exciting science, like for example, the detection of exomoons. We will look also looking for planets around the Wolf stars, like for example, red giants. And then we also have a complementary science program that is going to be organized through an announcement of opportunities that are going to be issued by ESA. And then the idea is to invite guest observers to make any proposal that has that has to do with any complementary science topic that does not address the core science of the mission. And then the idea is to reserve 8% of the telemetry allocation excluding calibration time to this program. And this implies a lot of targets. So then actually 8% may not sound a lot, but when one calculates this in terms of objects, it's going to be an impressive contribution to the mission. Okay, so which methods will PLATO use? Well, the first one, since PLATO is a high precision photometer in space, and then is the best photometer in space that will be built, then we'll be using the transit method. And then, as well as you all know, we are waiting to see the transit of the exoplanet in front of the star. And then this will cause a decrease of the light of the star. And with this method, we are able to determine the orbit parameters, the orbital inclination of the exoplanet, and also we'll be able to determine the planet to star radius ratio. So then this is also very important to emphasize that the method doesn't give us the planet radius, the absolute planet radius, but the relative planet radius with respect to the star, which means that if we want to know very well the planet radius with the precisions that I mentioned before, then we need to determine the star radius very well. And that's why PLATO will also be very important here, because it will be able to carry out astereosismology analysis of the host stars, of many of, not all of them, but with a large proportion of them. And astereosismology is a technique that looks into the frequency space of the light curves. And then the frequency space of the light curves shows us how the stars oscillate. And the oscillation of the stars is directly related to the properties of the star and to the internal structure of the star. And with models, we can make very good determinations of the radius of the star, of the mass of the star, and also of its age. And it's very difficult to determine ages accurately, especially of main sequence stars. And that's why the 10% that we want to achieve with PLATO is going also to provide a very key parameter to analyze planetary evolution and also how the stellar systems evolve. And then just to make a little bit an association, so we will be able to differentiate the different exoplanets in terms of the equivalent to the geological ages on Earth, because as you know, Earth has changed very much when it was formed, its atmosphere, its structure until now. And that's why when we look at an exoplanet, it's not only enough to see it at that moment, but also to know at which time we are seeing the exoplanet, because the properties may be completely different depending if it's close to this formation or is much later in its evolution. And we will complement these methods with the ground-based observations. And the ground-based observations will be done indeed for the filtering of false positives and also for the determination of the mass through the radial velocity method, which is, the radial velocity method consists of looking the spectrum of the star with very high precision. And because the star moves due to the influence of the planet around the star, so by this movement that creates a Doppler effect on the spectrum, so we can determine the planet mass that is indeed influencing the movement of the star. And then with this, we can determine also other orbital parameters, and then we cannot determine the minimum planet mass. But when we combine the minimum planet mass through the radial velocity method with the orbital inclination that is provided by the transit method, then indeed, then we have the bulk characterization of the exoplanets. And as I said before, we have accurate radius, mass, and age. Well, these are the reasons why we want to have PLATO and also the methods that PLATO will use. And from what I said before, so you can see that indeed PLATO requires a large field of view, because indeed bright stars are distributed in the sky in a uniform way. So the only way to look at many of them is to have indeed a large field of view simultaneously, but also requires to have a large total collecting area, because we want high sensitivity in order to achieve the precisions that we need. And since in space this is difficult to be achieved with a single telescope, so the approach that PLATO uses is a multi-telescope approach. And then here is represented with the 26 cameras that PLATO has. Well, looking at the characteristics of PLATO, so then it's a 3-axis stabilized system. It will be pointing, it has a launch mass of around 2,500 kilos. And well, the size I put here the measurements, but it's interesting that when the sun shield and solar panels are deployed, so then it will be a length of more than 9 meters. So then altogether it will be quite an impressive spacecraft. But what is important is that so far, with the current knowledge of planning and the current knowledge of the system, we have a launch date in the end, December 2026. And the launcher is going to be an Ariane 6.2. PLATO is going to an orbit around the second Lagrangian point, because there is where we can achieve the thermal stability that is needed indeed for such a precise mission. The consumables of PLATO are defined for 8.5 years. So this is also very important for what I will explain afterwards. And the spacecraft rotates every 3 months, because when it goes in the orbit, the sun may go into the field of view, and in order to avoid this situation, which of course is not good for the observations and not good for the detectors, so then the satellite rotates in order indeed to have always the sun shield and the solar panels towards the sun. Well, the prime industrial contractor for the PLATO satellite is OHB System AG, and then it works with a core team comprising Thales Alenia Space and Ruhr Space Switzerland. The payload. Well, the payload consists of 24 normal cameras. The cadence is 25 seconds, and then these cameras operate in white light. Then we have 2 additional cameras that have 2 filters. So one camera has a red filter, the other camera has a blue filter, and they work with a cadence of 2.5 seconds. The cameras are going to be used for science, but also they are fundamental for the pointing of the satellite, because they are our fine guidance sensor. And the PLATO payload is the responsibility of ESA in collaboration with the PLATO Mission Consortium. And the details of how this is organized are described in a multilateral agreement. Okay, so here just to have a view of how the satellite will be launched with the solar panels folded, and then it will unfold as you see here in this movie. And of course, there are other, like the main gain antenna is also going to be unfolded like this. And with this impression, at least you have a view of how the satellite design looks like. Well, something also interesting for PLATO, which is different from other missions, is the instantaneous field of view. So, well, as we said, it has to be large. So then the field of view has an extension of more than 2,200 square degrees. But not all the sky is seen by the same number of cameras. Some number of cameras. So here you have the numbers that indicate how many cameras each area will look at. So then the blue area will be seen by 6 cameras, the green area by 12, the red by 18, and the white one by 24. And then this is due to the fact that it's the best way to indeed look at a large area of the sky, and indeed, at least in part of this field of view, to have very high sensitivity, which is the center. So basically, the cameras are mounted in 4 sets of 6 cameras each, and have a pointing offset of 9.2 degrees. And it means also that it depends, so it's not only the magnitude of the star that is important, but it's also the place where the star is in the sky field that will determine the ppm, the sensitiveness that this star will be observed with. Okay, which is the PLATO observation strategy? Well, the nominal mission means the mission for which we have funding now is 4 years. And then the current baseline is to have 2 long pointings lasting 2 years each. We have possible alternative scenarios, like, for example, to have the first long pointing for 3 years, and then the 4th year going around the sky, doing a step and stare. But indeed, this is still not completely clear. The final strategy will be decided 2 years before launch. If you look here at this figure, then we see the galactic sky, and in blue, there are the two possible long pointings for PLATO that we can have. Actually, the center is determined by the pink line, so then the center has to be always in this area, because otherwise we violate the sign constraint. What is interesting to see is that the PLATO field, both in the north and in the south, can overlap the test continuous viewing zone, which is represented in yellow. And in the north, it will also overlap the Kepler field, as that is represented in pink. But what is also important to highlight is that the nominal science mission is indeed 4 years, but as I said before, the satellite is built for 8.5 years, which means that we can also ask for extensions to the Science Program Committee. And then if these extensions are granted, for example, we can ask already for an extension while we are observing the first point in the first area of the sky. So we may able to decide then, okay, we are going to stay longer in this first pointing, maybe 3 years, and then go 3 years to the other one, or even longer. So there are different possible scenarios that one can consider if it's already possible to ask for the extensions then, and then these are granted. Okay, an important also event that for the preparation of the mission, we think that is going to be very useful for both the amateur community and the professional community to know, is that next year we'll be announcing the first long pointing. So exactly the coordinates of the pointing, and it will be on the north or the south. And this will happen in next year in June. So by next year, we will be communicating this location of the first pointing. If you are interested in looking in more detail, for example, to All Sky PLATO input catalog, or how do we going to select the field? So basically, what is the figure of merit? What are the characteristics and the criteria that we are considering? So there are these two papers, one by Montalto and collaborator, and the other ones by Nassim Beni and collaborators, that are in astronomy and astrophysics. So you can go there to take a look. Now I wanted to go to the PLATO data products, just to very quickly to explain which products we have. Well, the first, we have level 0 products, which will be the images of selected targets. There we have in the test the Potsdams and so on. So then we have a very similar idea. So we select a region around the star, and we download this, which is the imagejet. But PLATO will not be able to download the imagejets of all the stars that is observing. So many of them will already have the light curves derived on board. And that's why the level 0, which is the raw data, already consists of imagejets and already validated light curves and centroids that are produced on board. Then we will have the level 1 products, which are indeed the processed image and level and light curves. And basically, the idea is to provide data that is already calibrated and free from instrumental effects. Then we go to the level 2. The level 2, this is a product. These are products that are different from other missions, in the sense that we are going to provide to the community the analysis of the asteroseismology, which includes all the characteristics of the star. We are also going to provide to the community the analysis of the stellar rotation periods and the activity. Also, we will be given already the planetary systems that are confirmed through TTVs. And on top, I highlighted here the planetary transit candidates. In this case, this is the same as for TESS or Kepler. But then this is, of course, very important for the amateur community, because they are, of course, this is the first list to start following up exoplanets. And we have, in addition, the level 3, we will also deliver level 3 products. And this is not for all the targets like the previous ones, but for a group of targets, what we call the prime sample. And then the level 3 is already the catalog of confirmed planetary systems combining transit and ground-based radial velocity observations, which means that for the prime sample, the consortium commits to provide and to organize the ground-based observations that will give the radial velocities for the determination of the masses. So then this is also a little bit different from previous missions. Well, now to understand how the samples of PLATO are defined and how are they going to be released. So if we assume two sky pointings, which is the baseline mission, then we have what we call the statistical sample, which is a sample of more than 245,000 dwarf and subgiant stars with a visual magnitude of less than 13. And this is extended to 16 magnitude for M stars. And then we have what we call in PLATO the P1, P2 samples, which is a smaller group. And these are the brightest stars. So then there are 15,000 dwarfs and subgiant stars with stellar types from F5 to K7 with a magnitude of less than 11. And for these stars, the requirement that gives if this star is in the sample or not is that the light curve needs to achieve a noise to signal ratio of less than 50 ppm in 1 hour. And for these stars, then are we going to be able, because they are brightest stars, to do the radial velocity determination, and also we will be able to detect the smaller exoplanets. But on the other hand, this doesn't mean that in the one of less than 30 magnitude, there are not going to be these smaller exoplanets, but it will be more difficult to follow them from the ground. Then we define the prime sample, and the prime sample is the name that we give to the sample for which we will do the final, indeed, the delivery of the level C products. And it will consist of these bright stars plus some of the statistical sample. And then we call it prime sample in order to be clear that it's not only the ones defined by the requirement. As I said, for the prime sample, we will provide the ground-based observation program and delivery of level C products. And then we will provide a list of these stars 9 months before launch, so people know which stars we are going to include in the ground-based preparatory program. Then there's also a group of stars that are proprietary targets of the consortium, and this is the small circle that I just represented here. Well, how are these data going to be released? Well, for the level 0, the level 1, and the level 2 data products, then they are all released per quarters, and then this is associated with a 3-month period that we have between the spacecraft rotations. And then for the statistical sample, the release will be almost immediate. So then for the first quarter of data, then we will release it 9 months afterwards, but this is just because it's the first one. And for the subsequent quarters, the data will be released 6 months after it is observed. For the prime sample thought, as we want to start already carrying out the ground-based observations, and also because the main focus will be the long-term, the long period planets, then for the prime sample, then the first quarter of data will be released 1.5 years after it's observed, and subsequent quarters will be released 1.25 years afterwards. So then this is just to have an idea of when people can expect to have the data. And then just I would like to finish indeed with some comments about how we see that the amateur astronomers can contribute. Also, of course, this is just a first list, a first mentioning of ideas, because I'm sure that there will be many other points where the amateurs can have very fantastic contributions to the mission. So, well, as you see, I mean, the ones, so the prime sample are the stars for which the consortium is committing to produce the follow-up. But then there are all these additional more than 200,000 stars that have magnitudes between 11 and 13. That is the PLATO legacy that will contain many interesting objects, not just exoplanets, and indeed will be completely open for the community. But I would like also to highlight that even for the prime sample, I mean, because 1 year it will be public, so then even for the prime sample, the community will have the opportunity to do follow-up. So then clearly a contribution from amateur astronomers could be on the larger planets, because this probably the resources of the professional observatories are going to be less dedicated. And well, and then it can be also that the contribution is for the filtering and also for the determination of the parameters. But also the amateur astronomer community can also contribute to the filtering of actual Earth candidates, because especially at the first stage, we need to remove the false positives, and we will need indeed filtering campaign with a spectroscopy. We will need also imaging resolution, because as we've seen before, the pixel of PLATO is 15 arcseconds, so then it's a little bit smaller than the one of TESS, but it's also large. Then we'll also have false positives from this point of view. Then another interesting point is the long period single transiting planets. So then this I've seen also that in TESS, they are also doing this exercise. The conference that I attended last week was the case. And then it means that we will have, of course, very clear transits, because PLATO is very precise of big planets, but then we will see only one transit. Okay, with this transit, we may be able to have an idea of when the planet comes back, but of course with large uncertainties. And that's why it will be difficult to follow this up with professional observatories, but then clearly with smaller observatories and with observatories for the amateur astronomy community, this will be very appreciated and will be very useful exercise. Then, of course, what we already discussed during other presentations, that indeed the ephemeris monitoring is very important, because sometimes the transits are not, depending if you don't have many transits, especially for the longer period planets, then the ephemeris are less precise, and then clearly you need to observe them more times in order to be able to improve the precision. And this is also very important, because we will have observatories like JWST, like Ariel, that are going to do atmospheric characterization. And in the same way, an exoclock, they need to know very precisely when the transit happens. They cannot afford to waste time waiting for the transit or missing the transit. And therefore, this exercise is fundamental. Another area where there could be also interesting contributions is on the monitoring of photometric activity. And there will also be citizen science opportunities for the analysis of the light curves. So just here, just to give some numbers. Maybe we don't need to follow all the scheme, but if we assume that we are going to have with 2 sky fields something like 1,250 exoplanets around stars that have a magnitude of less than 11, then probably we will start with a number of candidates that is twice this number. And then the first, especially 2 steps, which is the low precision spectroscopy and high resolution imaging, where we will be able to remove a large number of the false positives, then could also be contributions, as I said before, from the amateur community. Just to give some numbers, so we expect in general, so for all types of exoplanets and periods, around stars with magnitude less than 13, around 9,500 candidates, and around 4,600 confirmed exoplanets. And if we look at the larger exoplanets like Neptune and giant planets, the yield expected is around 300 exoplanets with magnitudes less, around stars with magnitudes less than 11, and around 2,000 around stars with magnitudes less than 13. We're still revising these estimates, but they will not be too different from the numbers I show here. And with this, I finish my presentation. Thank you very much for your attention. PLATO is not alone. I mean, we also have fantastic missions in ESA that ESA is leading or is contributing to, like CHEOPS, WEF, and also in the future Ariel. So we hope that with these missions and with the contribution of the observatories from the ground and the contribution from the astronomer community, we really will be able to make huge advancements in our knowledge of exoplanets. So thank you very much.